The topic for today is validation of deep learning. But before we talk about the validation, let's talk about the deep learning aspect of why do we even need deep learning and in what context are we presenting deep learning here. Through this, I'm just going to give a background on CMC, on the specific part that I am working on, and then summarize really the bulk of the progress in PIRE over the years. But then I really want to spend time at the end on the validation part. So this is something you've seen maybe from all of us, the importance of CMCs and their use cases in aerospace and even other fields. But what I really want to stress where my word goes is really understanding the effect of microstructure on damage of these composites. So I said CMC a few times and not everywhere. A lot of other people said that, but those are ceramic matrix composites, and they are, we know anything about ceramics, just monolithic ceramics, it's like your coffee mug that you drop and it cracks, and you certainly do not want to fly with that. So in order to achieve that toughness and damage tolerance, CMCs have silicon carbide fibers with a coating around them to provide that weak interface so that a material can break with cracks propagating through the matrix without damaging the fibers right away. So how do we get to this part where we understand the effect of microstructure on damage? And this is, my slides are advancing. All right, so the methods that we're using here is we're using synchrotron CT, so micro CT, very similar to the medical imaging, but just high resolution imaging of inside the samples. And on the left-hand side here, you'll see a rig that is complicated for the reason of running experiments at a realistic environment of these high temperature composites. So the rig here is able to provide loading, whether tension, compression, 4-point bending, and while doing that, heating up a sample at high temperatures, operational temperatures close to 1600 degrees C, and also controlling the environment within it, whether you want a control environment of water vapor or oxygen or an inert gas. So you're really trying to simulate a real world environment of how a CMC or what it would see on fields. So with that, you have a small opening here for non-destructive imaging. So you're doing all this loading, heating, and environmental testing while imaging non-destructively for about 3 minutes per load cycle. And when you get out of this, there's a lot of data. This is just one scan that is scanned of the sample before even loading, and it's about 2,000 cross-sectional images. So this is about 500 gigabytes before even loading the sample. So it's a lot of data in 3D. So you could section this and you get a cross-sectional view or a longitudinal view. And the aim here is trying to extract this data with an automated algorithm so that we understand where are the fibers, where are the matrix, and potentially where are the damage and how to model it. So going next, I'm just going to briefly summarize the 5 years I've spent and trying to understand what I've gone through now that I'm past that point. My first year was really developing the expertise to image the microstructure and damage using this rig that I showed earlier in that slide. And then the second year was really focused on automating the image segmentation process of extracting quantitative information rather than just looking at pretty images. In 2020, when we are all stuck at home, that allowed us to focus a little bit more on just extracting this quantitative information. And then Jonathan, where's Jonathan? Oh, hi. Jonathan and I worked on understanding the process of making a CMC, which is the polymer to ceramic conversion, HIP infiltration. The year after I tried a lot, well, I worked a lot on relating damage in composites to the microstructural features. I won't be covering a lot of this today, but I'll just give an overview. And then these 2 points over here, this is in collaboration with GE during my internship, where I'm trying to bridge the gap between experimentalists and modelers. And at the very end, which I'll talk about, is how do we validate these models? So to start with, these are our composites. They're silicon carbide fibers in silicon carbide matrix. And the only reason you could see them is because of the coating around them. They're exactly the same contrast. It's very easy to distinguish where the fibers are, the pores, and environmental barrier coating is in a cross-sectional view. But when you look at a longitudinal view, you're really clueless to what you're looking at. Yeah, you can guess that these are pores, EBC, but then you can't differentiate between a matrix and a fiber. And that actually becomes more important to see where the cracks propagated, whether it's in a matrix or a fiber. So the challenge here is real, where there is no grade level contrast between those fibers and matrices. And you're working a lot with this data. Just to summarize, these were 17 terabytes. And if you would go and analyze everything, it's just a lot of data. If I gave everyone in this room the data to work on it collaboratively, we would be stuck here for 360 years. I don't think it's a bad place to be stuck at, but it's not a really cool problem to be staring at a computer with. So similarly here with the cracks, you'll see that they're very small and they're within the resolution limits of CT. So going back to the main objective, which is trying to automate that process to effectively teach a computer what a fiber is, what a matrix is, and where are the cracks. So what we've done here is taken about 17 of these cross-sectional images and went through the manual labor of painting every single pixel, which I'm not too proud to say I spent 3 weeks of my PhD doing that, nothing else. But effectively, you're trying to train a computer to understand where the fibers are in the matrix, and then introduce a neural network that would look at these images and then hide them and try to predict them on the raw images. And it only trains on about 80% of the data. And then when it trains on these 80% and tries to do a prediction, then it looks at the 20% of the validation data away so that it could assess how well it's doing. So this process doesn't just happen once, it happens iteratively, where you train, assess, go back and learn. Train, assess, go back and learn. So this is about 3 computer days with this neural network. But what you get at the end is what you need is that you introduce a volumetric image. So this is 2,000 images, a stack of cross-sectional images laid together, and you run a model, and then a segmented volume comes up. So these are results of how the model operates on a cross-sectional view, decides where the fibers are and the matrices are, and then stacks them together. So you're actually now able to differentiate between the phases that you have, whether fibers or matrix. And these are just the potential in 2D. In 3D, really, you could be as effective as doing advanced visualizations and really eye candy here, where you strip off the EBC and just show the matrix and the fibers and try to understand where things are at. But really, this is just visualization. You want to advance more into the quantitative analysis, like fiber volume fraction, matrix volume fraction, and actually, more importantly, assessing pores and finding porous networks. So this could be even done more effectively now that we've segmented these volumes. Can try to investigate how thick of a matrix layer was deposited with a CVD method here. You can see it's a gaseous method in nature where the CVD is really thicker on the outside and then thinner on the inside here. And you can start differentiating between two groups of pores that are really enclosed by the CVI process. So these are enclosed pores here, and you'll see that the matrix is thinner versus the pores that are on the outside where the matrix was able to infiltrate in. And so far, we're just looking at pores in 2D. And if you would look at this separately, you'd think that these are just separated pores. But now with the power of this automated segmentation, you're able to know that all of these red dots here are a network of interconnected pores. And this becomes really interesting if you're interested in re-infiltrating with a polymer, like a polymer, or active cooling of these materials. So all of this has just been microstructure. You can also teach an algorithm to identify where the cracks are and pick up on the cracks, not only in 2D, but start visualizing them in 3D so that you can relate back to the micromechanics models of the crack spacing and how far the cracks are from fiber breaks. So to just continue on the summary from previous years, this is work that Jonathan did where we took images that were already there in 2020 from the synchrotron and tried to understand that pre-ceramic polymer to a ceramic conversion. So these are images from UC, University of California, Santa Barbara, where they took in situ images of how that polymer changes to a ceramic. These are images from 20 to 400C to even 1,000 you'll see here over a course of 24 hours. And you can start with these analyses to develop knowledge of how shrinkage cracks happen and how re-infiltration can occur from just one cycle and study that over different cycles. So that will relate a lot back to what Spencer is doing when you get thicker layers that you could understand the deposition of these layers and the formation of pores a little bit more clearly. Now that we've also applied these models, in 2021, we asked the question of, okay, now we're using a lot of deep learning models. How much training data do you need? Because that's the most expensive human time. So in order to answer that question, we should not limit ourselves to one image. So here are 4 different examples of composite images. This is the CBI, the polymer infiltrated. This is some synthetic data set, along with some 3D printed data. And we ran, for every run, for every of these images, we ran about 125 models to understand how many training images are needed. And the answer is not as satisfying, but it makes more sense where you need as many images depending on the complexity of a sample. So these 2 samples here appear to be more complex. So these are the CBI and the polymer infiltration, and they tend to actually plateau based on the one image that is fed into them. So those are the more complex samples. Therefore, those have the lowest score of accuracy after 250 training cycles. But you can then start learning that this is the CBI here. The more training images you add, so this is 1 ground truth, 2, 3, up to 20, the higher the accuracy that you'll get. So you'll start seeing a trend and actually a cost of diminishing returns here of where enough training is enough. So for this sample, it's about 4 ground truths will get you within an 80 to 90% accuracy. So I've been talking a lot about accuracy, and this is really the bulk of where I want to spend most time on, because I'm sure people will have questions about how do you validate these models. So the way we're approaching it here is using 3 different approaches. We can use ground truth from manually segmented images, those manually painted pixel by pixel, and try to compare the accuracy of models that way. The second way is just use synthetic data, we know where every pixel is, and no one has to really manually highlight those pixels. And then the third is using a high, like ground truth from high resolution optical images. So, and the objective here is to try to compare different validation methods by something that a materials scientist would care about, which is by fiber detection rate, and use these methods not only for validation, but for calibrating measurements. So the first method here is just the hand painting of the different pixels to identify where the fibers are. This is very laborious, and there is a reason people don't like that, but it will still remain useful at some point. But I'll introduce these images here. Whatever is green is an overlap between the fibers that were segmented by a human being and the fibers that the deep learning model is able to identify. In blue are the fibers that were segmented by hand, but the deep learning model was not able to pick up. And then in yellow are the fibers detected by the deep learning, but the human didn't even manage to see them. So you could see quite a discrepancy of this method, where this is the method that trains your model. How is it that wonky? It becomes a little bit worrying. And overall, you have about 89% of the fiber detection rate. So a big takeaway from here before I move to the other method is that validation by manually labeled images is not really a good metric for model accuracy. And this is what a lot of material scientists have been relying on. If you talk to the computer scientists, they're like, throw manually segmented images to the trash and let's do all synthetic images. Well, that's great. You have synthetic images that are replicating a CT scan of a fiber-enforced composite, and the images look quite similar, and they're defined quite nicely. So over here, this is the ground truth of where the fibers are in blue, and in orange, these are the predictions of a deep learning models of where the fibers are. And it's interesting that the fiber detection rate is 100%. So the same model that gave a detection rate of 89% for the different method gave 100% for here. So there's quite the discrepancy. Are you accurate by 90% or really 100%? And if you look really quickly at where the errors are for the segmentation for the synthetic images, you'll see that it's really at the edges where you don't really capture features of fibers, or you're at the edges of these fibers. So it's okay that these errors exist. But the error, the validation by synthetic images as a material scientist is really the best way to benchmark algorithms. So if you have different deep learning models, then you can compare them with different synthetic images. But later we learned that they're not really an accurate representation of fiber detection from what we saw in the previous method. So the next method here, this is work in collaboration with GE during the internship, is why don't we just take a really high resolution image of the same sample tested at the synchrotron, section it and take a high resolution and then overlay them together to see if the fibers that we can see from the high resolution matches the fibers that we see in CT. So the next slide here is the optical, and then the optical segmentation in green, and then the CT and the CT segmentation in orange. And you can sort of guess what we're going to do here is that we're going to overlay them on top of each other to detect a fiber hit rate, to see a fiber detection rate. And the detection rate here we define by the fibers that are segmented in CT and matched to the fibers in optical, divided by the total number of fibers that we are aware of. And you can see here that the detection rate is about 93%. So it's in between the manual segmentation and the synthetic data. So there's a story to kind of be cautious now of both extremes of a material scientist and a computer scientist, and try to marry both worlds in a way that you could get a more realistic validation method. If we explore more on the accuracy here of why is it 93% detection rate, you'll see that the deep learning can miss some of the fibers that you will miss by eye. So these are some fibers that you can see on an optical image here that are really faded away because of the thin coatings in the CT image. And now you can sort of believe a model. If a human can't really identify it, then you can cut the model some slack that they can't identify it. So it's good that the model is not making up where the fibers are. I'm not sure how well I'm doing on time, but we'll go through this last slide. So as a conclusion and summary of this, deep learning image segmentation seems to be effective for images of low contrast. If you have images that have high contrast, you'd rather go with conventional image segmentation methods rather than go through the hassle of deep learning. A lot of the work that I still didn't present here is that quantitative information from these experiments become very, very useful in calibrating and validating modeling efforts for these composites. And a quick summary here from the validation approach is manually labeled validation is not effective, but it will still remain the easiest way to train a model by highlighting the features that you see in an image to train a deep learning model. So every method here will stay for a reason. And then synthetic images will be the most effective in benchmarking deep learning, different deep learning models to compare between different models. And then the validation using high resolution optical images gives a close representation of your success rate and is good at calibrating measurements. However, it's a very laborious process and should only be done if you have a patch that you need to process for a very specific project. And with that, I hope I didn't go for very long, but we'll wait for questions.